All right, let's talk about how we actually evaluate these explanations right now. Just to be clear, I'm going to give you a bunch of examples of how people usually evaluate post hoc explanations, but in no way is it going to be completely thorough. So one of the questions that come up is, how do we actually evaluate explanations? And there's a paper here that has done a pretty good job of sort of putting it in a taxonomy that we can understand. At the very lowest level are the functionally grounded evaluation. These are ones where you try to test a very specific functionality, but try to sort of automate it as much as possible. So there are no real humans involved in this, and the tasks are usually proxy tasks. They're not exactly the real world tasks. A slightly higher level than that is human grounded evaluation, where you're definitely evaluating with real humans, since evaluating interpretability is a big part of it. But the tasks are a little bit simplified from what you would face in the real world. And the one at the very top is an application grounded evaluation, where you take your evaluation and actually deploy it with real humans on real tasks that they care about, right? And so at the very low level, you have the cheapest way of doing it. Then you have sort of crowdsourcing or user studies, the way you can recruit people, all the way to application grounded stuff. Of course, we want to get to the top, but there are practical constraints. Apart from the question of how we are evaluating it, which are these three different questions, we are instead going to be looking at a slightly different question of what are you actually evaluating, right? So what are you using the explanations for? Maybe we can divide evaluations based on that. So one reason you might be using explanations is just for a user to understand the behavior. Another one could be the fact that explanations can be useful for debugging. And finally, explanations can also help you make decisions, right? So in some sense, these three things are very different from the ones that ask about how we evaluate it. So you can imagine it as a conceptual matrix where any combination of these may be a potential candidate for evaluation. So in this section, I'm going to be focusing mostly on what we are evaluating rather than how we are evaluating it. And I'm going to just give an example of each of these so that people understand. So with the first one, the question is whether the user understands the behavior from the explanations, or if you don't have a user, then the question is, does the explanation correspond to what the model actually does? So one of the main questions when it comes up is, well, if you're selecting features and telling and sort of claiming that they're important or not important, how can we make sure that the features that are selected are actually important to the model? One way to do that is to just delete the most important features and see what happens, right? And so the idea is you would start with an image like this, which has some saliency map that has identified important pixels in this case. And you will essentially plot the prediction probability coming out of the model as you delete the most important features, right? So you identify the most important features, delete it, and see what happens to the probability. Take the next most important feature, delete it, see what happens to the probability. And you essentially continue doing this till some point. In some cases, people do it all the way till your whole image is basically deleted and you get your final prediction probability, right? And looking at this curve, you can judge whether the explanation was useful or not, or corresponds to the model behavior or not. Because if it is a good explanation, then this probability should fall down really fast. And if it's a bad explanation, the probability should not fall down that fast, right? And that way you can decide whether the explanation is good or not. People have, not that many, but people have also done the inverse of this, where they're trying to see if we can add the most important features. Does the probability go up really fast, right? So you would start with an empty image, and you're going to add some stuff to it, like the most important features according to your explanation, and see what the prediction probability is. And you will keep doing that till you have, some natural stopping point, or maybe you'll keep doing that till your whole image is present, and you'll get some curve, right? And again, in this case, you have a good explanation where this probability increases really fast because of all the features that are important that you've added. And if this curve doesn't increase very fast, that means you're adding features that the model doesn't really care about. And so that's a bad explanation. It doesn't correspond to the model. What has also been interesting is that this idea has also been used for training data. So if you remember, Julius talked about influential training points. Some explanations try to find those. You can also add or remove them from the training data and retrain the model and essentially plot the prediction probability to do the same thing. So here's an example from a paper last year where they're removing a fraction of the training data. But the order in which they're removing depends on importance coming from the explanation and seeing what the validation accuracy is. And if this curve falls down really fast, as it seems to be for this blue curve, that's a better explanation, or at least a better representation of what's happening inside the model. And they again have an insertion version where they're adding the most influential training points, retraining it, and seeing how the accuracy goes up. So these were sort of one way of evaluating the behavior. Here's another one that is pretty common, where you're trying to train the users to predict the behavior of machine learning models. It's also been called simulation by a few papers, and I'm giving some examples of where these things take place. The idea here is you have some data and some classifier that you're trying to evaluate, and you get the predictions and explanations for this data from the classifier. Right? So a bunch of predictions, false true, and then an explanation, whatever explanation technique you want to evaluate. And you actually show these things to a user. Here's the prediction, here's an explanation. They have some time just to look at a bunch of them. And the idea is for them to understand what the model, how the model behaves. Then what you do is you give them new data points. Don't show them the prediction, don't show them the explanation, just give them new instances and ask them to guess what the classifier would do on this new data set. And all they know about the classifier is through the predictions and the explanations. They make their guesses. What you do is you run the classifier on this new data, get the actual prediction from the classifiers, and compare the guesses with the actual prediction and compute an accuracy. And this tells you how well the user understands the classifier. If they're really accurate at this, then they've been able to simulate the classifier, and therefore the explanations must be useful. Here's an example of how it was used, where this is sort of what the UI looks like. This is a regression problem. So what do you think the model will predict? You give them they have to make a guess, and then they also have to talk about how confident they are, and both of those things are incorporated in the evaluation. Okay, so that was a couple of examples of how to understand the behavior of the models. Let's talk about how we can use these explanations for debugging, and essentially how that is a way to evaluate these explanations. There are 4 different ways of doing this. I'm going to sort of quickly walk through what they look like. In a lot of these cases, the goal is to create a buggy classifier. So in this case, that's what this bug on a classifier represents. And what you want to know is the user able to figure out what this bug is? So you synthetically create these buggy classifiers, or somehow you know that there is a bug in there. What you do then is you run the classifier through your explainer, generate either a bunch of explanations or whatever you need to do, show all of them to the user, and then you ask them. So here's an example of what that would look like. You can take the snow example and the wolf example that we talked about a long time ago, where the explanations are showing that the classifier is only looking at the snow. You show this to the user. You say, hey, for this image, the classifier predicts wolf, but this is what the explanation looks like. And then you ask users things like, would you trust this model? Right? And you basically measure how often they say no, because if they know it's looking at the snow, they shouldn't trust it too much. Second question you can ask them is, what do you think the classifier is doing? Just as a free text, explain to us. And then you can read it and evaluate whether they got it right or not, right? Whether they mention snow or anything like that. This is one way to see whether the explanations show you what's going wrong with the classifiers. Here's another way, which is a little bit easier to evaluate, where you create two classifiers. One of them is a clean classifier, the other one is a buggy classifier. You run both of them through your explainer, get two explanations, and show both of them to the users, often side by side. So here's an example of, And then you basically ask them, given these two explanations, which algorithm do you think is better? And you see how often they picked the clean one versus the buggy one. The more often they pick the clean one, the better the explanation is, because the user is able to evaluate how good a model is using just the explanations. So as an example, you can start with the wolf snow image again, and the explanations you would generate would look something like this, where the clean classifier is actually looking at the wolf, the snout, the ears, and the fur, and so on, whereas the buggy classifier is looking at the snow. The user should be able to look at these two and say, okay, clearly the first one is better and not the second one. The third way to sort of use these explanations for debugging can be thought of as fixing it, or actually improving the classifier. You can't always do this because of how feature engineering works, or I guess is often not present nowadays, but you can do that sometimes. So what you can do is you can take a buggy classifier. So for example, you can do NLP where there are some words that the classifier seems to be focusing on, and those are just noisy words that should be just removed. You run it through an explainer and you show the user the explanations. And in some sense, you get feedback from the users by asking them, what do you think looks wrong in this explanation? What do you disagree with? What features is the model looking at that you wouldn't want it to look at? And you incorporate this feedback somehow into the training process. So for example, you could just remove the features that they think it looks wrong. Right? Some way to sort of change your training objective or change your model to do that. And you can sort of iterate over it. You don't have to do this just once. You get a new classifier, you can run through this again, and essentially compute the accuracy of the classifier on some held out data that you trust, that you think is clean, and you show that the accuracy is going up. So even though the user may not know feature engineering directly, may not know much about machine learning, they're still able to annotate these explanations to give you a better classifier. The last way of using explanations for debugging can be thought of as finding errors in the training data. So in this case, this mostly applies to prototypical explanations, or when it's sort of influence-based stuff, where the explanation is trying to find important instances from the training data. In this case, you can start with the training data, the original clean training data, and then add a bunch of instances that are deliberately wrong. Right? So you can even take a bunch of instances from the original training data and just flip their classes, whatever you need to do. Run this through your classifier, run this through your explainer, and remember the explainer here is one that finds important points from the training data. So you show the users the most important points, and you essentially ask them to relabel it. Right? You say, okay, here were the most influential points, relabel it. And I guess the hope is that if the explainer is accurate, is correct, clearly the noisy instances will have a big impact on the classifier, and therefore they should show up higher in this ranking. And then you can just evaluate, were the ones that were added, the noisy ones, were they the ones that were selected by the explainer? And does the accuracy go up when you relabel those points, right? So even though I have a human here, you can imagine easily automating this whole thing, where you just look at the highest ranked ones and put the correct label in there.